So, tartaric acid. Tartaric acid, it forms meso compound. So, this is due to the presence of plane of symmetry. So, this is the structure of tartaric acid. Okay? COOH, CHOH, CHOH, COOH. Okay? 2,3-dihydroxybutanoic acid. Okay? So, here 2,3-dihydroxybutane dioic acid, that is tartaric acid. Okay? So, two COOH groups are there. So, here it having plane of symmetry. So, this plane can separate tartaric acid into exactly two equal halves. Okay? So, due to the presence of plane of symmetry, it does not exhibit optical activity. Even though it having the chiral carbon, this is the chiral carbon which is surrounded by 4 different groups around it. Even though it having the chiral carbon, it does not exhibit the optical activity. So, this is called meso compound. Okay? Then, mixture of two enantiomers in equal concentration which does not exhibit the optical activity, that mixture is called Racemic Mixer. So, this compound is meso compound. So, that means it contains 50% dextro and 50% levo. Okay? So, mixture of two enantiomers in equal concentration present in a same compound. Two enantiomers present in a same compound and does not exhibit the optical activity. Okay? So, such type of mixer is called Racemic Mixer. For example, tartaric acid forms Racemic Mixer with the 50% dextro and 50% levo. That's why Racemic Mixer of tartaric acid, that is expressed with the formula like this: plus minus Racemic Mixer. Here plus indicates dextro, minus indicates levo. Okay? Next. So, conversion of enantiomers into Racemic Mixer. So, process of conversion of enantiomers into Racemic Mixer, dextro and levo enantiomers. Okay? So, they into Racemic Mixer, that is called racemization process. Racemization process. So, conversion of enantiomers into Racemic Mixer is racemization. Separation of enantiomers from Racemic Mixer. Separation of enantiomers from Racemic Mixer, that is called resolution process. Okay? So, different terms are there. So, racemization is the conversion of enantiomers into Racemic Mixer, whereas resolution is separation of enantiomers from Racemic Mixer, that is called resolution process. Okay? Then, some organic compounds are there. So, compounds which does not contain any chiral carbon atom, they also exhibit optical isomerism, when they are not having chiral carbon, but exhibits the optical isomerism. So, that is due to overall dissymmetry in their structure. Okay? All dissymmetry in their structure. For example, allenes. Allenes are dissymmetric compounds. Okay? So, this is allene. Okay? So, carbon, 3 carbon atoms. So, if you consider the middle carbon, it is surrounded by double bonds on either side. Okay? Then, so allenes exhibit optical activity due to dissymmetry in the whole structure. Okay? Next, coming to alkylidenes. One of the double bond in allene, that is replaced with cycloalkane. Okay? So, this is also exhibit optical isomerism due to dissymmetry. Okay? Then coming to spirenes. If both the double bonds are replaced with cycloalkane rings like this. Okay? So, they are spirenes. So, they also exhibit optical isomerism due to dissymmetry in the structure. Next, biphenyls. So these are the biphenyls. Biphenyls exhibit optical isomerism due to dissymmetry in their structure. And one more thing is they are having substituents at ortho position. Okay? Substituents are present at ortho position. This is steric hindrance. So due to steric hindrance, they exhibit the optical activity. Next, calculation of number of optical isomers. If a compound is unsymmetrical, okay, so unsymmetrical molecules. So first coming to calculation of optical isomerism, number of optical isomers in unsymmetrical molecules. So here we can calculate number of optically active isomers, meso compounds, meso isomers, and also racemic isomers. Okay. So first coming to number of optically active isomers. So that is equal to 2 to the power n. Okay. So where n is number of chiral centers or number of chiral carbons. Okay. So this is for unsymmetrical molecules. Calculation of optically active isomers. Okay. Then coming to meso compounds. So meso compounds for unsymmetrical molecules, that is always 0. Okay. So meso compounds, number of meso compounds, that is equal to 0. Next, number of racemic isomers. So number of racemic isomers, that is equal to number of optically active isomers to the power 2. Okay. For example, if you give symbol A to this, okay, number of optically active isomers. Okay. So here we can write number of racemic mixers as A square. Okay. Then coming to symmetrical molecules. So for symmetrical molecules, if n is even, number of optically active isomers, A is equal to 2 to the power n minus 1. A is equal to 2 to the power n minus 1 when n is even. Okay. And meso compounds, number of meso isomers, M is equal to 2 to the power n by 2 minus 1. M is equal to 2 to the power n by 2 minus 1, meso compounds. And racemic mixers, R is equal to A by 2. A by 2. Okay. Next, if n is odd, so for odd number of compounds, we can write number of optically active isomers, that is A is equal to 2 to the power n minus 1 minus 2 to the power n minus 1 by 2. Okay. So 2 to the power n minus 1 minus 2 to the power n minus 1 by 2. Okay. So this is for n is equal to odd. Okay. So meso compounds, number of meso isomers for this. So that is 2 to the power n minus 1 by 2. 2 to the power n minus 1 by 2 indicates meso. And R is A by 2. Or A by 2. Okay. So, this is for symmetrical molecules where n is even and n is odd. So, here also no, A by 2 only, not A square. A by 2. Okay. So, this is the calculation of optical isomers. Now, let us see some objective bits regarding isomerism, geometrical and optical isomerism.